I mean, I threw this problem up here, but it's, I don't know, maybe it's kind of stupid. I mean, what's step one of doing a limit?
Plug it in.
Plug it in. If you plug this one in, what's your answer? 1/4. So there's nothing mysterious. It's a nice, easy question. And the fact now that I'm approaching 2 from the left actually has no significance on this problem. Guess what? The answer is still 1/4.
Right.
Do you understand that? I mean, it has no... I mean, technically it's a one-sided limit, but when you get to 1.999999999 and plug it in, you're darn close to 1/4. So the answer is 1/4. So there's I'm pointing out that there's times when the coming from the left or right don't really even matter that much. There are times when it just doesn't matter that much. But again, this one's a 1/4. There are times when it matters. There's times when it matters. Let me. This is all of a sudden, I'm jumping up to 2.5 for this question here. Check this out. The limit as x goes to 6 from the right, 5x minus x squared all over 6 minus x. So this time this is a good problem. Okay, and I just jumped up to 2.5. I did one of these last class before we left. Step 1, let's plug it in. See what we get. 30 minus 36. 30 minus 36. A negative 6 over 0. By the way, I'm just plugging in a 6. I know it's 6 from the right, but I just plug in a 6 to see what's up. And that's what's up.
Right.
Listen, so a famous limit answer has been 0 over 0. And when we get 0 over 0, we've been trained to try to fix it. What happens here at the end of the chapter, there's some of these problems, we get a number over 0. And from your algebraic days, a number over 0 is undefined. But in the world of calculus, a number over 0 is a number divided by a teeny weeny 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 number is huge. A number over 0 is infinity. I'd like you, in limits. In calculus, when you're doing limits, a number over 0 is infinity. Now the debate is whether it's positive infinity or negative infinity. That depends on the signs of the numbers. I know he's negative. What about this little 0? Is this little 0 on the right side of 0 or on the left side of 0? Well, here you go. You're approaching 6 from the right. So if you're on the right side of 6, you're like a 6.001. So pretend this is a 6.001. When you sub 6 minus 6.001,
You're the right side too.
no, I think it's a little negative.
Right, so go to positive.
So I'm on the negative side of 0.
Right.
So this little 0 is, again, I'm looking at this 0 as a teeny weeny number, and I just figured out that it's a negative teeny weeny number. So I'm going to put a little negative sign on my 0. You've never seen anybody do that.
Yeah.
0 is usually 0. But I'm saying it's a teeny weeny number on the negative side of 0. If that's negative and that's negative, the ultimate answer is positive infinity.
Yeah.
I knew the answer was infinity, but I had to dissect whether it was positive or negative. So here's a problem where coming from the left or right is a big difference, and you really need to pay attention and analyze it big time. But I'm calling this positive infinity. This is also a nice one to do, to try to do with your graphing calculator. I mean, but it's kind of a pain. It's always a slight pain to pick up your calculator and type this crap in, make sure it's typed in correctly. But you could put in parentheses on your numerator and your denominator. You could type this in. You could take a look at this. One thing you should remember, I think, and know from algebra is that it's got an asymptote it's got a vertical asymptote at 6. That's the other reason this answer is infinity. I mean, I explained it analytically, kind of numerically, didn't I? Now I'm explaining it visually. This function's undefined at 6. It has a vertical asymptote at 6. as you approach 6 from the left and right, you're going to head toward infinity. Right? That's what asymptotes do. That's what vertical, right? See, sometimes everything's so obvious to me, and I'm staring at you. Guys don't look like you're getting it. I don't know. It's okay. But I'm talking fast. I know I'm talking fast. But from your algebra days, when this thing's undefined at 6, ain't that a vertical asymptote? Thank you. Isn't it logical that when you have a vertical asymptote, the graph, when you approach that, the graph approaches infinities, either positive or negative? Right. So I'm explaining the visual, graphical reason why this is infinity. There's an asymptote there. And, you know, again, I don't know, you know, I don't know these graphs all that well, but I do know they head toward infinity, or negative infinity, but I don't know which one was which. I don't know which one was which, unless my graphing calculator would have told me. Well, after I did this problem, I know, hang on, after I did this problem, what did I learn? That when I approached 6 from the right, the answer was positive infinity. So, okay, so this picture is accurate. I did draw this accurate. I bet you from the other side it goes down. You don't have to do it graphically, though. I taught you how to do it by plugging in a little 6.001. To me, that was nice and logical and easy. But you got to get used to thinking of a number over 0 as some type of infinity. But let's get back to this continuity just a second here. I want to find another one of.
I'd like to have an example of a piecewise function.
Yeah, I know.
Did you number 18?
Yeah, maybe. Okay. Let's do number 18. So 18 is a piecewise function. And it's kind of nasty. It's x squared minus 4x plus 6. X squared minus 4x plus 6 when x is less than 3. And it is negative x squared plus 4x minus 2. Negative x squared plus 4x minus 2 when x is greater than or equal to 3. And their question is, what's the limit as x approaches 3? Now, the question isn't even about continuity. I mean, we need to get there. That comes up next in this section. But at first, they're just making me do some limits. Anyway, they're asking for this limit. And there's only one way to do this limit. The way to do this limit is to do 2 limits. You have to. The way you do this limit is you have to go investigate the limit as x approaches 3 from the left. And then you have to investigate the limit as x approaches 3 from the right. That's the only way you can do this limit. Now let's just say they both come out to the same answer. Then what's this answer? That answer. Yeah. Let's say they come out to different answers. Then this answer is does not exist. That's what we've learned. But the only way to do this limit is to go do those 2, especially in a piecewise function like this, right? So anyway, now I'm doing this limit from the left. From the left means you're on the left side of 3, and I would just basically plug a 3 in there. And plugging a 3 in there, and I think it's 3.
And if you wanted to put a 2.9999, you can.
You could plug in a 2.9999 if you wanted. And you would get something darn close to 3. But you should call it 3. Because that whatever 2.9999 you do, you can get closer. See, the answer is 3. The limit is 3. You know, the concept always was this. This is approaching 3 but never getting there. And then the y value is approaching 3 and never really getting there. But we call it the answer, even though it never really gets there. We call it the answer. 3, because it's a limit. Anyway, what about from the right? From the right, I pay attention to this. I'm on the right side of 3. I plug it in here. positive 3. Now that's a negative 9. That's a 1, I think.
Yeah.
Did you get 1?
Yes.
All right, cool. So now I know the answer to this question. What's the answer to this question?
Does
The
not
end.
exist.
Right. Yeah, that's a good problem. See, again, is there people, listen, how do you know which one to use? Why is he plugging it in there and then he's plugging it in there? I mean, do you understand that I'm paying attention to this? This is the key to these problems. When you're less than 3, you're on the left side of 3. That's why I use that. When you're greater than 3, you're on the right side of 3. That's why I use that. Yeah. By the way, go ahead. Go ahead.
How did you get the 1 again?
Well, I plugged in a 3 here. So I got negative 9. See, you square it first, you get 9, and then it's a negative.
Okay.
So it's a negative 9.
So you wouldn't do negative 3?
No, it ain't negative 3. Look, who's being squared here is the x, and that negative sign is out in front of the x. That's a common mistake, but the negative sign is not being squared. So it is not negative 3 squared. No, it's not. It's negative 3 squared, which means do the exponent first. You get 9, and then you negate it, you get negative 9. Yeah, that's probably the issue. Negative 9 plus 12 minus 2. Yeah, that's how I got 1. What was I going to say? Oh, this question was just a limit question, and we figured it out. But let's discuss continuity for just a second. What would you say about this function? It's a piecewise function, and what would be your conclusion about continuity? It's discontinuous. Where is it discontinuous? I always want to know where. And when I say where, it's an x value. It's always an x value. It's discontinuous at 3, right? This 3 here where, yeah, it is. You're right. How come it's discontinuous? Because the left and the right didn't line up. I mean, there's a picture. I don't want to get the specific picture, but generally, on the left, it was one thing, and on the right, it was something else. Remember, these two limits were two different things. So there's a big break in this graph. When I do these two limits, I can tell that, yeah, they don't line up. It's discontinuous at 3. By the way, because there's a break and the limit didn't exist, we use this word to classify this as non-removable.
Yeah.
This question wasn't about continuity, though. It was about do this limit. Then I changed it. I added to it.
Yeah, that's not piecewise.
Look at this one. Here, actually, I'm making one up. You ready? So this is 2, 4. Look at this. And I want to know about the continuity of this. Please discuss the continuity. Discuss isn't really good. Here it is. Here it is, here it is, here it is. 5x squared minus 6x all over x. No, sorry. I'm sorry, I'm so sorry. 5x squared minus 6x all over x squared minus x. Whatever. I don't know. This is okay, but it's not that great. What's the question? Find all the points of discontinuity and tell me if they're removable or not. So you should know that the discontinuities happen when the function's undefined a lot of times, not every time. But so the function's undefined when, when the denominator is 0. So I'm all about figuring out when this denominator is 0. I'm going to try to do some factoring. I think I'll factor the numerator. Can you factor the numerator? You can factor an x out.
Right.
It's so simple factoring, people lose it sometimes. You can factor an x out, and you're left with 5x minus 6. What about that denominator? Can you do any factoring? You can factor an x out. And now that it's factored, I'm staring at the denominator, and when is this function undefined? And therefore, these are both, if it's undefined, these are discontinuities. What are they?
X equals 0.
X equals 0.
And x equals 1.
And x equals 1. They're both discontinuities because they make the function undefined. The original function is undefined at both those places. But algebraically, you can clean up this one guy here. You can cancel this guy away, but it doesn't make him not a discontinuity, but it does make him, he's a hole and he's an asymptote. That's exactly right.
Right.
Because he cancels away, he's a hole in the graph, and he's a vertical asymptote. I'll use that word. He's a hole. He's an asymptote. No, he's a hole. And he's an asymptote. He's a vertical asymptote. He's a hole. And we called those holes removable. And we called the asymptotes non-removable. And that's funny language, and I never did explain that language very great. I mean, but just memorize it. It's funny language, removable, non-removable. I don't know how to make much sense out of that language, but it's two types of discontinuities. Discontinuities can be classified into these two types. So cool, we did this problem. That's kind of easy. And in a way, I didn't use my three-step definition of continuity, but in a way I did. The first step of my three-step definition is the function has to be defined. And so, the first thing I was doing was looking for where the function was undefined. So I found the places where the function's undefined. Those are the places where it's discontinuous. Right. I'm going to remind you of this definition, and when I give you the quiz, I think I'm going to leave it on the board here. I'm going to say this, f of x is continuous at x equals c if, and here's this three-step definition. F of c has to be defined. The limit of the function as x approaches c has to have an answer or exist. And the third criteria is whatever your answer to number 1 was has to be equal to your answer for number 2. So I'm going to say that the answer from number 1 has to equal this answer from number 2. And if you pass all 3 of these tests, what you're doing is you're investigating a specific x value, and if you pass all 3 of these tests, then it's continuous at that x value. Doesn't mean it's continuous everywhere. Maybe you got more x values you need to investigate. But maybe not. Usually, well, let's do one. Let's do one of these. Watch this. So, here's one. Boy, oh boy. When I start getting creative, I get creative. All right, this is a hell of a great problem. It's a function. It's called piecewise. It's split into 3 pieces. Do you understand that?
Yeah.
It's got 3 pieces. Let me just as a general outline, what's going on is at less than 2, it's doing something. Less than 2, it's doing something. By the way, it's actually a line. It actually doesn't look like this. But less than 2, it's doing something. You understand?
Yeah.
Okay. Between 2 and 4, between 2 and 4, it's doing something. And then on the right side of 4, it's doing something. And what I'm really concerned about is what's happening at those places 2 and 4. Is this stuff matching up, and is it continuous or not? You follow me? That's the question. And so is it matching up at 2? Is it matching up at 4? That's basically the big question. Let's just look at something though. So when you are this function and you're less than 2, do you have any issues when you're less than 2? Is there any other issues to worry about? Any other undefined places? Say no.
No.
No, right. It's a line, right? There's no undefined places to worry about. No. When you're in between 2 and 4, look at you. You're a nice parabola. Any places to worry about, like 3 or 3.5? Or no, you don't have to worry about those. You're nice continuous. Between 2 and 4, you're cool. Look, when you're greater than 4, you're this dude. Is there anything to worry about when you're this dude?
Yes.
6. 6 is a bad place. Does 6 happen when you're greater than 4? Yeah, 6 does happen. I mean, yeah. Are you with me?
Yeah.
All right, so I told you I was worried about the 2 and I was worried about the 4, but I also stumbled onto this. You got to watch out for this.
Yeah.
6 is also a bad place. And I already know the answer for 6. Can we just spit it out? 6 is, oops, I don't want to erase that. I want to go ahead and say x equals 6 is an asymptote, isn't he?
Right.
I mean, he's an undefined place. He doesn't cancel away. There's no factoring or canceling. He's a vertical asymptote, so he's a discontinuity. And what do you call him? I know I said he's an asymptote, but he's non-removable. Good job. Good job. And I didn't really need my 3-step definition for that. You understand? I mean, I guess when x is 6, it's undefined. That is sort of the first part of the definition. Right, it's undefined, it's discontinuous. All right, let's investigate the 2, man. I want to see what's happening at 2. So now I'm investigating x equals 2. I came over here where I got some room, and I'm going to do my 3-step definition. So step 1, what's f of 2? What is f of 2? And that means you got to plug 2 into the function and see if you... Well, where do you... So pay attention to the equal sign.
Right.
See, you can't plug 2 in there. I mean, not for f of 2. For f of 2, x is 2, and that means you're right here. X is 2. X is allowed to be 2 here. So I'll plug a 2 in there. And what do I get?
-47.
Good. 4 times 10 is 40 minus 87, and negative 47. Thank you. Number 2 says I better do the limit as x approaches 2 for this function. Well, if I'm going to do the limit as x approaches 2, I'm going to have to go investigate the limit as x approaches 2 from the left. Am I talking fast? The limit as x approaches 2 from the right. I mean, that's how I got to do it. I got to go investigate these 2 limits to see if this even exists. I kind of doubt it does. But let's do it. That means I'm doing 2 from the left. If I'm going to do the limit as 2 from the left, I'm going to plug 2 in here.
5 minus 16.
5 minus 32.
Yeah.
Negative 27?
Yeah.
Negative 27.
2's from the right.
If I'm doing the limit as x goes to 2 from the right, I got to pay attention to this. I'm on the right side of 2. I plug a 2 in here, and I already did that, and I know the answer is negative 47. And so I just learned something. This limit does not exist. And then I just learned that he's a discontinuity. And which kind of discontinuity is he?
Non-removable.
When the limit does not exist, he's non-removable. That's pretty good, you guys. Did you follow that?
Yeah.
I'm doing my little three-step definition of continuity. It helps a lot. It helps a lot. Logically go through this little definition. So I got that answer, I got that answer. I still need to investigate 4. Let's investigate x equals 4. I'm investigating x equals 4 here. Here we go, step 1. I need f of 4. I need f of 4. What's f of 4? Oh my god. Alright, I gotta plug a 4 in here, right? Because it's where it equals. See where the equal thing is? Okay. 4 minus 4 is 0. E to the 0 is 1 times 6 is 6 plus 2. That's 34. Following me? Over 4 minus 6 is negative 2. 34 over negative 2, I think? Negative 17. Woohoo! Now I should do the limit as x approaches 4. What that means is I got to do the left and the right. I'm getting a little sloppy. See me getting sloppy here?
Okay.
But I'm going to do the limit as x approaches 4 from the left. From the left, you're on the left side of 4, I think. When you're less than 4, you're on the left side of 4. So you try plugging a 4 in here.
Okay.
160 minus 87. 73.
Okay.
When you're on the right side of 4, you plug a 4 in here. And we sort of just did that, and we got that negative 17. And therefore, this limit does not exist. It didn't match up. And he's another discontinuity. Are you guys okay?
So you would say
Non-removable. Thank you.
non-removable, right. So we had to check that third one to see. Two answers.
Well, that's enough. That's enough of that stuff.